Hello and welcome back. We're about to look at a concept that is actually going to be used not just today, but also in all of the stuff we're going to be talking about on Monday. And so this is a concept called Hess's Law, and today we're going to look at one application of it, but on Monday we're going to look at two more applications of Hess's Law. But this is what we're looking at today is what's considered the classic Hess's Law calculation or usage of. And so what Hess's law is, it's based on the fact that delta H is what's called a state function. And because it's a state function, it only applies, the delta H can be calculated um, if if we know like a series of reactions that would sum up to essentially the overall reaction. And we sum up these reactions in mathematical way. Since delta H is a state function, and this term state function just means something very, very simple. It means that the total enthalpy change depends only on the initial state of the reactants and the final state of the products. And so this is like a kind of a difference between temperatures in the evening and so the difference in this is like the difference in temperatures in the evening and temperatures in the morning. Those two things, the difference between those two things, let's say we have two different days, day one, and day two. Okay, so in day one, what happens is we start out at 60 degrees C. No, it's Fahrenheit, not C, that'd be crazy. And then the temperature jumps up to 80 degrees Fahrenheit. And then at the end of the day, it drops that back down to 62 at midnight the next night. Okay, so this is morning, or say midnight. This is afternoon on day one. And this is next midnight, so midnight. So we'll go through this cycle. If we were going to calculate a delta T from midnight to midnight, what we would do, all we would have to look at is essentially the 62 Fahrenheit minus the 60 Fahrenheit. And the answer would be just 2 degrees Fahrenheit difference, right? Now imagine that we actually did a similar type of thing with day two. So we're looking at day two, starts off at 60 Fahrenheit. Actually, no, let's actually even do a different one. Let's say it starts off at 62, jumps up to 90, then drops back down to 64. If we do a delta T here, we would see that it's 64 minus 62. And so the change in temperature is equal to 2 degrees Fahrenheit. The same number. These are just two different calculations, right, of difference in Fahrenheit from one midnight to another. There's some differences in the middle between what happens, but it only matters what the initial and the final temperatures are. So changes in variables are almost always state functions in that the actual value only depends upon the initial and final kind of state of the whatever we're looking at. So total change of enthalpy in a similar way, erase that so we can look at it, is independent on the number of steps that we take to get to the eventual chemical product. It only depends upon what we're starting with and what we end up with. And this actually allows us to do some really, really interesting things mathematically. But what it means kind of from a conceptual standpoint, and I know this is a scary looking figure, but when you look, when I describe it, I hope it doesn't look as scary after we consider this. So if we're looking at a chemical reaction, this is methane burning, because it's combustion reaction, making CO2 and water in liquid state. The delta H for this reaction is actually really, really hard to determine experimentally, because what happens when we burn stuff, we don't get a liquid state water, we actually get gaseous water at the end. because we don't have pools of water generally around campfires. We do have smoke, and part of smoke is water vapor. And so looking at this thing, this chemical reaction, in order to calculate uh, the actual change here, because it's easier to, instead of going directly from methane and O2 gas to CO2 and liquid water in one step, the delta H, if we could do it, we would calculate it as being negative 890 kilojoules, again, per, say, mole of methane or 2 moles of water combusted this way. But in the way that this is actually determined, generally speaking, is you get the initial measurement of the heat, calculate the delta H for the reaction of going from CH4 to O2 and making water or gaseous space water. And then you take that gaseous space water, you collect it and see what the heat exchange is for going from a gas phase down to a liquid phase. And if you add up these two different delta H, so delta H1, and actually let's call this delta HT, and delta H2, delta H1 plus delta H2 equals delta HT. It just equals the sum of those two things. Now, this has been verified multiple different ways experimentally. It seems like this is always true, but let's see what a chemical problem or a problem on an exam might look like. So, and it could be something this short, right? We see all these chemical reactions. You might be looking like, oh my goodness, this is super complicated. So we have a chemical reaction that we're trying to find what is the heat, delta H, or the enthalpy of this reaction, the heat exchange when we take 1 mole of N2O and 1 mole of NO2 and make 3 moles of NO. And so looking at this, we are given actually 3 different chemical reactions, and we're going to have to combine these in such a way as to get this overall reaction, this what I like to often call and will refer to as the desired reaction, and then these are just the given reactions. All right. So when we're adding them together, we're going to add them like we would a series of equations. So you remember in, say, algebra, you have A plus B going to make C, and then we got, say, B plus Y going to make Z. Then you can combine equations, say A plus 2B. Oh wait, hold on. We gotta actually make this have the same thing. So we can actually combine the two equations to say, well, we got A plus 2B plus Y goes to make 2C. So this is actually, it's got to be true here. And so these combination of equations here, this allows us to, we're going to add these chemical reactions or chemical equations together in a similar way. So I just showed there. So, and then there's some really useful hints about this. So I'm only going to give you on an exam equations that you need to use. It's very difficult if I give you some, say, red herring equations. Very difficult indeed. And so one of the things that you can do, kind of a strategy here, is look at the desired reaction, identify what chemicals are in it, right? Just kind of look at the chemical formulas, and then try to find those in the given reactions. If you find a single chemical, say N2O, if you found that in, say, reaction A and reaction B, then kind of ignore that one. But if you find a chemical N2O in only one of the reactions, notice that. Kind of look at it and see how it's different in the desired reaction versus the given reaction. So if we look at N2O, right, we're looking at all 3 of our reactions right here. The only place we see N2O happens to be in equation C. But there's a difference. There are a couple of, well, there's only one real difference between the N2O in C and the N2O in our desired reaction, and that happens to be the coefficient. So we don't want to use this chemical equation. We actually want to use half of the chemical equation to make that coefficient the same coefficient here, because we're going to eventually add these chemical reactions together. And so if we put N2 N2O, and I'm going to mark this as 1/2 C. We'd have N2O going to make N2, and then plus, because we're dividing this by 2, we divided that by 2. Oh no, we don't have anything to divide by 2. Well, remember there's an understood to be a 1 here, an invisible 1 or an assumed 1 for the molar ratios here. And since this is these kilojoules are on per molar basis, right? 2 moles of this goes to make 2 moles of that, 1 mole of that, and this much heat. We can actually use a 1/2 mole in these thermochemical equations because they're always on a per mole basis. You can't use 1/2 molecule, but you can use 1/2 mole. And so we will end up with plus 1/2 O2. All right, looking at the next chemical, so we've identified N2O, right? Now we need to look for NO2. And so in our chemical equations, the only place we find NO2 is in equation B. Now we got 2 problems with this thing. First, in equation B, this thing happens to be on the product side. In our desired reaction happens to be on a reactant side. Well, there's a thing we can do where we can say we're reversing the reaction. Because of the way energy is conserved in these chemical reactions and matter is conserved in these chemical reactions, we can assume that if we do the opposite of the reaction, take NO2 and make O2 and NO, we can actually just say that instead of this being an exothermic reaction with this much heat exchanged, it'll be an endothermic reaction with that same amount of heat exchanged. And so if we're looking at this, right, we reverse the reaction, we'd get that on the NO2 on the reactant side, the NO and the O2 on the product side. Now the other thing is we also have a -2. And so what I'm going to say is this is -1/2 B. Okay, so looking at this, doing -1/2 B. So we would have NO2. Now we notice I don't have a negative sign here. I just flipped reactants and products, going to make NO plus 1/2 O2. Right? So this is right here, but half of it. This is right here, but half of it. This is right there, but half of it. And then the last thing we need is the NO. If we look at our 3 different chemical equations, we only find it in one, which is nice because that means we can focus on just A. In this case, oh, that's not true. We do not have it in just one. We also have it in B, right? So if we got NO and B, which we did 1/2 B, so now NO is on the product side down here, that means we need 2 more NOs on the product side when we add A together. Well, if we look at A, we already have 2 NOs on the product side, and so we're just going to use equation A as is. I'm just putting A times 1, or A would be just fine there. So looking at this, we would write down A. We have N2 plus O2 going to make 2NO. Now, let's sum our equations together. So if we add our equations together, a couple of little things. So when we add them on the same side of the reaction arrow, we just add the coefficients. Got to be the same chemical to the right. O2 adds with O2, just like X would add with X, but X does not add with Y. And so we're looking at this, so we'd have O2 plus O2. And so we'd have 2O2, or excuse me, not 1/2. It's 1/2 O2 plus 1/2 O2, which is just 1/2 plus 1/2 is 1, right? And then we got plus 3NO plus N2 on this side. Then we've got N2O plus NO2 plus N2 plus O2 on this side. Oh, now we're going to do something kind of similar to what we did with the spectator ions. If you notice, N2 is here, but it's also here. If it looked like N2, at least it would be there, right? Well then, since it's on both reactant and product side, that means the N2 just kind of stays around during this 3-step reaction. It just doesn't do much. The O2, same thing. It just stays there. We can cross that off. And now we got N2O plus NO2 going to make 3 NO. And if you look at this equation, it's the same as our desired equation above. So that actually lets us know that if we do these kind of things with our delta H's and sum them up, we should get the right delta H. So again, what did we do with equation C? That's this equation. We multiplied it by 1/2. So we're going to have to multiply or divide this thing by 2, right? Multiplying by 1/2 is the same as dividing by 2. So this is delta H3 divided by 2. Now, C. I should have put delta HC because A, B, C, right? Now looking at B, what we do with B? We just multiplied it by negative 1/2. So all of a sudden, we have to do negative 113.1 kilojoules over 2. I guess I could have put the negative down there and that would have done the same thing, and so this is negative delta HB over 2. And then we're going to look at A. What did we do to A? We didn't do anything to A, right? We just added it to the rest of the equation, so that's what we do with the delta H. So delta H just by itself, or delta HA, is just 180.7 kilojoules. So now we do our math right here, and we take the 163.2 divided by 2. So it's negative 81.6 for this sum right here, plus 113.1 divided by 2. Notice I already, hold on, 113.1 divided by 2. So this would be 56.6 kilojoules. I accidentally cleared in my calculator. I'll have to do that one again. And so we got 163.2 divided by 2 negative plus 56.6 kilojoules plus 180.7 kilojoules. And so what I got, hopefully I did my math right, 155.7 kilojoules of energy are exchanged in this overall reaction, so that would be our delta H for the reaction, 155.7 kilojoules. And so now we see that this is an endothermic reaction, and it's actually got quite a bit of energy exchange there. All right, so there are a couple of Chem 101 problems. They're slightly simpler than this because I think on those I only have 2 given equations. But this is the only video for today. So Monday we're going to go on with some more Hess's Law stuff. This is not an easy thing, so please come to the conference, ask all the questions you need, and we could probably have some more practice problems if you'd like. So if anybody asks for tomorrow, I'll add some practice problems in Chem 101. All right, so I will talk with you guys tomorrow. Hi everybody, I realized after I hit stop the video, I forgot to mention, go do a practice problem, right? So Chem 101, so related to this, on Chem 101, hold on, there we go. Problem set 5 in your homework, or excuse me, in the homework tab on Chem 101. Make sure to go do that, because again, you want to make sure that you at least have a basic understanding. And come to the conference tomorrow, especially if you want extra practice or if you would want to do a couple more just, during the conference time. So anyway, I will talk with you tomorrow.